So let me start. I'm Chirag Ghosh, and I'll be talking about assertive programming today. So what is it? To give a fair overview, it is a principle of writing code which is based on fail fast. That means, suppose there is some problem with the code, or like there are some bugs, or we have made a mistake. We don't want that particular program to run wrongly, so we will just terminate it at that time, the time at which we see that there is some problem with it. We will just terminate it, nothing else. So let me just take it. uh, Now to speak like that, like we want our code to assert itself. That means, suppose we write a function, so it takes some input, maybe parameters, and gives a return statement or something like that. It does some work. So for input we need something, then the function will assert that I need this type of data type, or something like that, or this range of data. So if you give some other type of data, or like out of range or something like that, the code will crash. So why, like, we don't want our code to crash, but we are doing it explicitly to crash our code. Why? It is done so that suppose there is a problem, uh, in only that time it will crash, and when it will crash, we know that there is some major problem in our code, we need to fix that. So we will explicitly break the chain of coding at that time, and then we can easily fix that. This does the advantage that suppose there is some wrong data, it will not go down in line to make problems anywhere else. It is from my personal experience that I will be writing something. I have done some coding in JavaScript, then I will be debugging. Um, there will I will see problem in a particular function, then I will when I debug for hours, I will see that the problem is in another file. It happens sometimes. So this type of assertions can fix those problems very easily. Also, another aspect of assertive programming is that assertions are used to find conditions where something which we never thought would happen. Like, we assume sometimes that suppose there is a function, there are two types of variables coming. Those variables will have certain ranges or data types. We sometimes we just assume them, but they may not happen. Also, sometimes our assumptions would be looking like very much yeah, it should happen, but it doesn't happen. Like, I was reading a book called The Pragmatic Programmer. There was a chapter called Assertive Programming. I got some really interesting impossible things which happened. Like, these are the four things. Can anyone tell how this happens? Like, okay, I got one or two, like, but I got it was very interesting for me. So can anyone volunteer to tell me if, like, suppose any of this will happen? Hello.
No, I didn't understand the
Last
question.
one cannot have can break if its triangle is not made by triangle is hyperbolic geometry. It will be greater than hyperbolic or
Yeah,
what's the other
something like
case?
that. Yes, something
Last
like that.
one can break, and third one can break if you consider relativity.
Okay,
Uh,
I did not think
That
that.
depends on your definition of minute now.
Yeah, like, okay, like, there is
okay, but
less time,
fourth
so
one
I
is
will.
clearly it is possible. But one, two, three seems
Yeah,
okay.
like, there is less time, so I'll take you to the answers. The first one is completely history, but if you don't know, then you cannot tell. Like, September at 19 days. Second one, actually, I guess maybe it is some kind of alias, as it is stated. The third something, it is called leap minutes. The fourth, as Rakar said, there are some kind of geometry, non-Euclidean geometry, where, like, it may not be equal to 180 degree. For example, if a triangle is put on the surface of a sphere, then it won't be it is not a plane. Basically, it is not the type of geometry which we generally study. So why did I say these things? Like sometimes we assume things to work some way and they don't. And like in coding, it sometimes happens that we do mistakes, we don't see them, and down the line it can cause problems. So what we do is we put assertions. That means we suppose in the starting of a function it is called precondition statement or something like that. So we check that the state like the data which we get, it is right. Now this assertive coding is very much necessary in dynamically typed languages. I think I should define what is dynamically typed languages. They are basically languages in which the data type of a variable or a kind of data which we get, it is checked at runtime, as opposed to statistical type languages such as C, C++, Java, where we it is checked at compile time. Let me show you a thing. Here are some codes. I will show you the Python code because Python is dynamically typed. As you can see, okay, A and B are some variables, C and D also. Like we may get those from outside. Suppose A is equal to 0, then we are adding a string to an integer. It will not happen now. This particular statement will not take place because A is not equal to 0, and we won't get any error. As you can see, but I also have a C code. Okay. Okay. Yes, there's a C code. It is like equivalent to it. I have not used C and D variables and all. Now, if I try to compile it, we get a warning that we are doing a typecasting which is not explicitly determined, something like that. We get a warning that something is wrong. So like we don't get in Python. Now if I change that Python code to 1, then it will that A is equal to 0, then it will immediately show a problem. So like sometimes it happens that the conditions for which we will be checking our code, they might not be sufficient. So like we can do something like that, or something like there is a assert function which checks if this particular thing is correct on like it a boolean statement. So when we do this, it will show an error because it does not satisfy. And we suppose this type of debugging is generally done in development. So we generally people do not want these assertions to remain in production, because you don't want your code to like break in production. So you can just uh, and it works. The same code it works without the assertion. Like the assertion statements won't work. You can like change that. Suppose okay. So there are other programming languages like R where you can this assert function is also available. Okay, so now as we have got a type of idea about assertive coding, let's get into what it is not. Assertions are basically used to check problems or bugs which are caused by the programmer. Now, assertion is not error handling. For example, we are creating a login page. Now, if the user input some wrong, invalid data, we don't want our app to crash there, right? It's we cannot say that it should be always correct. So we should not use assertions there, because instead of that we should take it gracefully and show some other informative messages. Assertions are basically used in development where we will check for our own problems. That's it. With that, I think my talk is complete. I will end with some memes, and thank you.
Thanks, Chirag. That was quite nice.
बीम्स वाला स्लाइड वापस जाना,
Okay.
नहीं देख पाया सारे।
अबे सारे मत पढ़ा भाई। पढ़ते जाएगा, रुकेगा
4 ही
जरा।
तो है, 5 है।
हाँ बस प्रोग्राम। अच्छा, अरे ये क्या कौन सा सब रेट है वो? प्रोग्रामर
अरे
यूनिट।
/programmer
मुझे
हाँ।
ये वाला सबसे अच्छा लगा।
तो उसमें जो आई थिंक पाइथन में एक फंक्शन लिखते वक्त यू कैन डिफाइन द टाइप्स यूजिंग कोलन। आई गेस दैट वुड बी आल्सो एन एग्जांपल ऑफ
Uh,
असर्टिव प्रोग्रामिंग।
या लाइक इफ वी लाइक बेसिकली हमको डिफाइन करना होगा
हाँ
कि यही होगा, लाइक इट्स काइंड ऑफ ए डिमांडिंग सॉर्ट ऑफ थिंग, वी डिमांड थिंग्स इंस्टेड ऑफ आस्किंग।
राइट 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 राइट।
या सर्च टेस्टिंग के लिए ना मोस्टली,
हाँ हाँ हाँ।
कोड के बीच में इंसर्टिंग।
Also, like I was reading the programmatic programmer here. There, the author wrote, "Okay, it is done for development, but the author advised that put that in production too with nice messages." Then he gave an example that there was some company which did it, and after some years, their software got very robust.
नाइस।
Like although that that is not generally preferred, आप एंड यूजर को वैसा क्रैश करके तो नहीं दिखाओ, बुरा मान जाएगा।
कल हम लोग ऐसे बात कर रहे थे इन आई थिंक ईशान टॉक अबाउट डिजाइन प्रिंसिपल्स अबाउट Go is very strongly against assertions. It doesn't even have an assert statement because वो चाहते हैं developers handle errors instead of asserting and then moving on. तो उनका एक doc है on why assertions are not a feature in Go.
Do you know how I got this topic?
From ये guide क्या?
अरे like I was working on the project ना, like project है इसमें राकार तो थे उसमें, राकार साइल थे। Like the person whom I was working with, Abhishek, he is also like alumni of IIT KGB. I think मैंने जो कोड लिखे थे वो थोड़ा सा like समझना मुश्किल था और कभी-कभी क्रैश हो जाता था। Like sometimes I used to work in a feature, after 2 weeks the problems arose. Then he actually gave me this blog, a blog that was written by a developer of Elixir programming language, the founder I think. तो उन्होंने दिया था कि ये ले, ये पढ़, ये देख, ये एक टाइप का प्रोग्रामिंग होता है। लाइक Elixir is like strongly for it supports assertions.
अच्छा, nice. वो blog है तो भेज दो.
हाँ भेज दूंगा। या
I think पता नहीं, मेरे को ऐसा लगता है कि after a point you start using so many assertions that your code is just full of assertions.
हाँ
Instead of
मतलब
like
you can easily overdo it.
हाँ. The only place I've seen assertions in code is in tests. बाकी किसी ने कहीं देखा है क्या? Code
हाँ
में ऐसा
लाइक assertions एक्चुअली बहुत पुराना टेक्निक है। नाउ लेटली दे आर बीइंग कन्वर्टेड टू यूनिट टेस्ट्स। लाइक यूनिट टेस्ट उसी मतलब वैसे ही काम करते हैं। I read somewhere like I don't have that much information. Like Stack Overflow में लिखा था कि like assertions are now being changed to like unit tests or something like that. But the underlying principle is the same.
makes sense. मतलब you move your assertions to tests then. You want your assertion statements to be inside tests instead of code, I guess. I don't know.
Okay.
कुछ और क्वेश्चन है तो नेक्स्ट चलते हैं. I heard about Haskell. Right. There's always one functional programming guy. हम लोग कल रात को डिस्कस कर रहे थे.
Next, I think is Ananya.
Yeah, so I'll go next. Let me share my screen. Is it visible, my screen? If anyone can give a confirmation, the screen is
Yeah.
visible.
Yes.
Yeah, so hello everyone. So today I'll be talking about GDB, the GNU debugger. Uh, so here's an outline of what I'm going to discuss about today. So first of all, I'll talk about the basic GDB model, how to start GDB, how to set breakpoints, how to step over the program, how to examine data, and how to set watch points, as well as like, how to examine the call stack. So here's the basic GDB model. So we have just started a debugger. So a debugger process is made. You can also call it the GDB process. The debugger process uses fork to clone itself into two processes. Process on the left is the parent debugger process, and the process on the right is the child debugger process. Now what happens is the child debugger process replaces itself with the process that is being debugged. The debug process is also called the inferior process in the language of GDB. So when you get a message within GDB which talks about the inferior process, it's the debug process that is being referred to. And here by process, we mean a program in execution, obviously. So what does the debugger process do? So when you interact with the debugger using certain GDB commands, I'll talk about these commands shortly. It has the ability to read those commands, understand them, and execute them. The commands could be any one of the following, like for example, a command may want to see some information about the state of debugger itself, or it may want to know information about the debugged process. So the debugger process helps to show these informations to the user. It also helps in the setting breakpoints, and then it passes control over to debug process to start or resume execution by issuing certain commands. I'll talk about breakpoints a little later. So that's what essentially a debugger process does. It initially interacts with user, obtains certain commands from the user, and executes them. And in the process, sets some breakpoints in the debug process and starts the execution. So the debug process starts executing now. Its only job is to run till it reaches a breakpoint or it comes to an end. At this point, like when it comes to a breakpoint, things are engineered in such a way that it is forced to hand over control back to the debugger process. So the debugger and debugged processes execute in an interleaved manner, passing control to each other until the process ends. So that's the big picture. Now I'll go through some basic commands of GDB, what are their functions and syntax associated, and then I will debug a very small simple program called buggyproc.cpp using these commands. So one of the things that I would like to mention here is that the debugger works only with the compiled code or the executable. So normally when we compile, we use G++, then the file name, and then the executable name with minus O. But since we want to debug this program, we need to use a flag minus G over here. There are some other flags too, like minus GGDB, but I'll just stick to minus G for now. Uh, so why is it that we compile using the minus G flag, you may ask? The reason is that while the debugger works with only the executable, it has to relate the executable with the source program. So I have only the executable in hand. It consists of only machine instructions. But then at some point of time, for the convenience of the user, I have to relate what I have with the source program from where this executable come from. So like questions like what are the neighboring programs of a program statement centered around some particular line number in the code, let's say, or the addresses of the machine instructions for some statements or expressions that we have written in the code, or the types of variables we are using, and the and in which memory address these variables are stored. So questions like this, minus G flag equips the executable with such information which enables the debugger to answer our questions. So now how to start the debugger? We can start it by just giving the command gdb buggy prog over here. I'll just briefly talk about this gdb buggy prog.code so there's this really irritating error called the segmentation fault. So this error can happen because of many reasons. It generally has to do with accessing memory that is not allowed to be accessed. So actually, segmentation fault is the reason how I got to know about GDB. So I was searching about upon some ways how to debug this segmentation fault, like on Stack Exchanges stuff, and I got to know about GDB. So I thought I would mention it here. And simply to run the debugger, we can use the command run. But just running the command just after starting the debugger isn't really very useful. How we make it useful is by setting breakpoints, which I'll talk about soon. But before I talk about it, I'd like to like mention what the cycle of activities that is that takes place during debugging. So we set one or more breakpoints, and obviously setting breakpoints is a matter of judgment. Like if we set too many breakpoints, then the program will stop more often than it needs to, and if we set too less breakpoints, then we might miss out on the bug only. So yeah, but after we set the breakpoints, we run the program to stop at one of the breakpoints, and we examine the data around it and see if we can find the bug there. If the bug's found, then it's well and good, and if not, we just continue the execution to the next breakpoint, and this cycle just continues. So now coming to breakpoints. So actually breakpoints are those places in the program where we want the execution of the program to stop temporarily. To set breakpoints, we can just give the command at like break 43 if we want to stop the command at line number 43. Let's say if we want to stop the is to give a breakpoint at some other function other than the main function. So we use some other variations like GDB break, then the function name, and yes, and then we can give the particular line number in that function that we need to set the breakpoint upon. So yeah, that's that. And let's say in a long code, if we have given like 10 breakpoints, so we can get all the information about these breakpoints by just giving the command info breakpoints, which I will show when I debug the code in a little while. So to reach the first breakpoint, we give the command run, and to reach subsequent breakpoints, we can just give the command continue or C. So we can also do stepwise execution. Let's say we are at line number 33 in a command. So by if we use the next step, so next command, so it will execute the current instruction and go to the just the next line. So it will now go to the line number 34 and examine the code over there. And next, the step function, it is useful for a step command. It is useful for stepping into a function, and finish is helpful to continue to go to the end of the any current function, let it be main or any other function that we are having. So this is a little important. So sometimes what happens is, especially when there is there are recursive programs, you find yourself deep into the function which has been called recursively, and then this is where the where command or the backtrace command, if called, will give you the entire call stack, like all the functions that have been called so far. So let's say you have a very long code which has like 50 functions which call each other like arbitrarily. So after some time, when you're deep into the code, you want to know that how you got into that place, and you want to know how the functions called each other till there. So you can just backtrace, give the command of backtrace, and you will get the entire call stack over there. um, and this list command is really simple, really. Like let's say there's a breakpoint at line number 13. So if we give the command list, so it will give the code lines from, let's say, line number 10 to line number 16, like the neighboring code lines, program lines are around a particular line number. We can also examine values at any point during this debugging session. Like we can give the like both the print and display actually gives the value of variables at any point in the code. But the only difference is print will give the value, will showcase the value only once, while display will give the values at every step of the code. Like we continue it, and the display will keep on showcasing the variables value that we have given. We can also set some watch points which breaks when the value of an expression change, and we can give some conditions according to our needs. So I'll just debug a very simple program over here. So this is the program. It's a very simple program. So basically in this program, I want to find the value of this expression over here, like x to the power 0 by 0 factorial plus till x to the power n by n factorial. So it can be easily calculated that for x equals to 2 and n equals to 3, this value should, the value of this expression should come out to be 6.33. But when I compile and run this program, I'll give the value of x and n as 2 and 3 respectively. The value comes out to be 3. So there's some bug in this program. So I'll start the debugger by giving the commands that I discussed in the slides. So I'll just give the -g command over here, -g flag, and then start the debugger. So yeah, so the debugger has started. So as we can see that in this line number 43, the series value is being computed. So I would just like to set a breakpoint here in line number 45 just before the cout statement is going to be executed. It's sort of like a hit and trial. Like it's a like clever hit and trial, I would say. So break 45, and then I would run, give the values. So we can see that this code has stopped at this first breakpoint, which is at line number 45. And now, let's say I want to know the value of series value at this point. So I will just give the command print series value. And it comes out to be 3, which is wrong, that we know. So yeah, so this code is at fault. But here in this main function, we can see that there's nothing much. Like there are a few like cout scene statements, and it's pretty like obvious. So we can safely say that the bug is somewhere here in these two programs. So in these two functions. So I'll, let's say, check this function, the compute factorial function over here. So as I said before, like to set a breakpoint in a function, I will need to give the command break and then the function name. Yeah, so a breakpoint has been set, and it's this breakpoint sets the breakpoint at the line number 5, where the function starts. But if we see this function, that in the line number 13, it is just going to give like return the value of product, which is nothing but the factorial n, which is the argument of this function. So I will like to like keep this give the breakpoint over here in this line number 13. So I'll give it break 13. Yeah. So at this point, let's say I want to know about all the breakpoints, information about all the breakpoints. So I can just give the command info breakpoints. And we can see that there are 3 breakpoints that I have made, and the first one is at line 45 in the main function, and the next two are in the line 5 and 13. So at this point, like the first one was of no use, and I wanted a breakpoint at line number 13 only in the compute factorial function. So I can just delete the first two breakpoints. And now if I do info breakpoints again, then we can see that only one breakpoint is now left at line number 13. So now I'll just run the code. And since the code was stopped at line number 45, it's asking me to start it, like compile it from the beginning again. So I'll just say yes. And give the values of x and n again. So it is now stopped at the breakpoint line number 13. So here I would like to display the value of n, which comes out to be 0, and display the value of product, so that I can know or verify if product is n factorial or not. So 0 factorial 1, it works here. Then I will continue again. So here something is wrong. It's coming out 1 factorial is 2. I'll continue a few more steps to see what the problem is. So 2 factorial, it's coming out to be 6, and then again I'll continue, and it's coming out 3 factorial to be 24. So we can say that product is coming out to be n plus 1 factorial instead of n factorial. So it's safe. So we now know that the lies here in this 5 to 6 lines of code in this function. And it's really easy to say because I have given the counter value 0 here, and the counter is running till n and then counter plus plus. So the product is actually becoming n plus 1 factorial instead of n factorial. So I can just change here n minus to n minus 1 and save it. So I'll have to compile it again and check if the bug has been solved or not. Before it, I will just give that function backtrace to show you like what happens when this the functions are called iteratively. So here we can see that at lowest level the first the main function is called. Then at line number 43, as we can see, the compute series values function is called with the argument value x equals to 2 and n equals to 3. And then again at line number 21, the compute factorial function is called. And in this way like we can this is a small code, only three call stack is there. But when the processes are lengthy, like in lengthy recursions and stuff, this backtrace command is quite useful. So now I'll quit from this debugger and check whether my code is running right or not. So I'll decompile it again. And so yeah, so now it's coming out to be 6.33. So yeah, so my code is now debugged. So there are some advanced GDP stuff too that I'm not going to talk about today. But if anyone's interested, they can actually search upon it. Like working with code dumps. This is something I mentioned briefly. It has to do with the segmentation fault thing, and writing printer stuff and discovering memory leaks through Valgrind. And that's all from my side. Thank you.
Awesome. This was really cool. Thanks, Ananya.
Thanks.
There are some advanced usage of GDB. I don't know if you have noticed or not. So what you can do with GDB is that if there is a program running in some remote server, you can connect to that program using GDB and load the symbol table from a local version of the executable, and then you can debug the program running on a different machine.
Yeah,
That's
like
a
there's
pretty
some
cool.
command like control x a, like control plus x plus a, like that's how, like in the terminal only the code runs.
Sorry, couldn't get you. Can you repeat?
Uh, like I might not have gotten you, but I like in the terminal only we can get the code right. Like there's some command, I think control plus x plus a, so that gives the like the code comes in the terminal only. We don't have to go to any IDE or stuff.
Okay.
There's this really good tool called CGDB. It's like GDB, but it'll open a split terminal where the above, like the upper part, will be the file which is getting debugged, and it scrolls through the file. So if you set a breakpoint at line 10, it'll go to line 10, highlight that line, etc. It's like an amazing tool to use with GDB because you see the file like live being debugged instead of just remembering line numbers or having to see the code separately.
Yeah, that's what I was talking about. Like, can I share my screen again? Like, this function I was talking about was uh,
Yeah, so
just a
like
second.
you had the code open in another window, right? Like
Yeah, right. But I can just, that's what I was saying, that there's this command that we can just open the code in the terminal only. Like, just a second.
yeah. Yeah, so what CGDB does is it just splits that view into a top and bottom. And it's a Vim editor, so you can edit like as if you're editing Vim live. Change the file, run it again.
Okay, so like here I think. So this command, like control X, actually, like this is what we're talking about, right? like something like this. So in terminal only it comes.
Yeah, exactly this. It shows like where the
Yeah,
breakpoint is with the
yeah,
mask
like
line numbers and stuff.
yeah, like in GDB too, it's possible. Like I got to know about it recently too. Only like I didn't know it
Oh yeah,
before.
even I got to know it right now. Awesome.
Yeah.
Ananya, nice presentation about debugging tools. So I'm curious, do you have an example story where you really any debugger like really helped you? So I have like maybe 5 stories, and I know कि उस point पे print statements were not helping out. I had to use some debugging tool. So do you have any examples so far in life where you're like working on some project and a debugger helped you out? It's fine to say no or
No, actually, only a few days back, I was like doing some implementation of a data structure. I think it was AVL. I think so. There, I was getting like segmentation fault. Like I say, I don't know, thousands of times. I think so. Then I googled upon like how to like overcome this segmentation fault thing. So there, like in some comment in some like Stack Exchange, I think so. There it was mentioned the GDB thing, so I searched upon it a little bit. So like I haven't really done much
nice.
stuff with this. Yeah.
Yeah, totally. I mean, I used to give up at those moments, so I never really got the chance to use it. Yeah, that makes sense. I think it'd be really useful then. Print statements would be like, क्या print कर रहा है? Not really sure. When you're accessing some location, some data
Yeah, it
somewhere.
was like some pointer problem I was doing. Like I was like I had to create some new memory, like something, some stuff like that. But yeah,
Yeah, makes sense. Makes sense. Thanks.
Uh, okay, so I'll go next. The lightning talk. Am I audible?
Yes, go for it.
Yes.
I hope my screen is visible.
Yeah.
So in this lightning talk, I'll be discussing about data compression algorithms. Okay, so let's start. So let's just try to find out an answer. Why do we actually need data compression in the first place? So one of the obvious solution answer is because storage is scarce, and one more answer can be that when we send data through some medium, there might be that medium consumes. I mean, we have to give memory very after making many decisions. I mean, you just can't send up a whole book of data through some medium and expect it to, be received at the other end very finely. So um, the thing which we'll be exploiting in data compression will be redundancy, because it is present everywhere. We have this tendency of using the same data again and again in a document or anywhere else. So, and also it is better to store 100 A characters as 100 A rather than storing all the 100 A's in one bit, that sort of thing. And what data compression means is encoding, restructuring, or otherwise modifying data in order to reduce its size. So fundamentally, it's using some other notation or representation than the original form, so as to reduce size or hope to reduce size if there is redundancy present. And a good example of this occurs often with image compression. So the general idea is, let's say you have this very big file of data, and there's actually very large amount of redundancy present. We'll be converting it into a new notation. So, and then we'll be sending this. So there'll be two agents involved: the encoder and the decoder, the sender and the receiver, and both of them will be working with the common paradigm, common algorithm. And the encoder will, the job of encoder will be to convert this big file into a very light paper with the algorithm also, a way to decode it, and we'll send both of these things to the decoder at the receiver's end, and then we'll be decoding the message. Okay, so what is the breadth of this area? So there are like plethora of algorithms already present in this field. There are both types of lossy algorithms and lossless algorithms. And a brief history we talk about, you can you can see that shorthand was developed in 1000 BC, and then Braille code, and then Morse and onwards. Analog compression. The two algorithms which I'll be discussing in this lightning talk will be Huffman coding and dictionary-based compression. I had included arithmetic coding also, but then I thought that this presentation will become very very big and boring because I'll be talking about many algorithms. Okay, so let's talk about sending a sample string. So we know that typically a card data type uses 1 byte, which is 8 bits in form of its ST code, and there are a total of 128 characters. I mean, in the ST code, and it is helpful in case if we are using all the 128 characters in form, if you have to distinguish between them. But in practical scenarios, we're not using all 128 of those ASCII codes. In practical scenarios, we are rather using a subset of them. So, like for example, if you're writing an article in English, so most probably you'll be using the first 26, the 26 alphabets of English and with some punctuation marks. So we don't actually need to use all those 8 bits and actually store that data in the original form. We can come with a new notation to reduce its size. So the whole idea is that a lot of space is getting wasted. So of course, one such possible solution is to assign binary numbers to characters. So let's say A goes to 000, B goes to 001, C goes to 010, and all the characters, the unique characters that you're using in your document, we can assign them binary numbers, and we can attach this little dictionary that we found with the message, and then tell the decoder how to decode it, and we'll see how exactly it is done. So first thing that we'll be discussing is fixed size coding. So let's say this is a string, a sample string with a lot many letters, B, C, A, B, something like that. So first we'll be finding the unique characters which are appearing in the string. So there are 5 unique characters, A, B, C, D, E. So now we'll be assigning binary numbers in ascending order, and to find out how many bits we'll be requiring per symbol, we'll take log of the size of the unique characters to the base 2, which is 2.3 to 1, and then take field of it because we are dealing with discrete numbers, hence 3 bits per symbol. So A goes to 000, B goes to 001, C goes to 010, D goes to 011, E goes to 100, and we can encode the original string in this form. Right now, analysis. Of course, we have to send this data. So final size of the message, as you know, this string is 20, it has 20 characters. And if we're assigning 3 bits to each character, we'll be using 60 bits to, store the size of the final size of the message. And of course, we'll have to send the table and the set of unique characters, because how will the decoder know that it has to use A, B, C, D? So we'll have to send them in its original form, the ASCII form. So 5 unique characters account for 5 times of 8 bits, that is 40 bits. And the binary codes also. So we are using 5 codes, and each code is 3 bits long, so 15 bits. If we add it up, we get 115 bits. And this is obviously, better solution, because original string size was 160 bits, 20 times of 8. If we are using 8 bits for each character. So we have actually, achieved appreciable amount of compression through this method. Now, after devising this algorithm, of course, mathematicians had to go further and improving this system. How can we improve this system? So this paradigm actually depends on the premise that it is using fixed number of bits for each unique character, hence treating all the characters equally. So we are assigning 3 bits to each character, A, B, C, D, E. So what if we could come up with a strategy that okay, so the letters which are appearing more number of times, we can try to allocate them less number of bits, and which are appearing less number of times, we can try to allocate them the maximum amount of bits that we have to that we have at our disposal. So the characters which are having high redundancy should use less bits, and therefore more compression is possible. And one such algorithm which achieves this is Huffman coding, and it can actually achieve maximum compression possible with prefix codes, and it is an optimal algorithm. So let's try to take a brief introduction to how this algorithm works with the same example. So actually not the same, the same example. So what we'll be doing is I've written down a table, and I've written down a table in the increasing order of the frequency of the letters which were appearing in my original string. So E appeared 2 times, A appeared 3 times, D appeared 4 times, and so on. And now we'll be devising a strategy to assigning codes to these characters and assigning them very carefully. So the first step would be to arrange the letters as such in the increasing order of the frequency. Now the algorithm goes like this: you have to select 2 nodes which have the least number of weights attached to them. So we'll be choosing E and A because 2 and 3, these are the 2 most minimum weights of the list that we have right now, and then add a node connected to both of them and add the weights and assign that to our new node. So 5. And then we'll be continuing it, the whole algorithm. So as you can see, E and A have been done for at this step. So the new node that has been added in the list is 5, and the remaining list will be will contain D, B, and C. So we have to continue this. So now what are the 2 most minimum numbers that appear in front of us? So it will be 5 and 4. We'll add them and connect the new node 9, and we'll add continue the whole thing till we reach the root. Right. So what we've got in front of us is a little binary tree, and this is a tree which will help us in deciding how many bits do we have to assign to each character. Right. So the next step would be to assign 0 on the left edges and 1 on the right edges. So as you can see, on the left edges of each node, I've assigned 0, and on the right edges, I've assigned 1. Right. Now to find the code, all I have to do is start from the root, and I'll have to take turns left and right, and note whether 0 is appearing or 1 is appearing until my character is reached. So for E, you can see I'll start from root, I'll take a left turn 0, I'll take again a left turn 0, I'll take again a left turn 0. So E will be assigned 0, 0, 0. Same for A, it will be assigned 0, 0, 1, D 0, 1, B 1, 0, and C 1, 1. One thing to ponder about is that naturally the letters which appear most number of times, they ended up getting most closer to the tree. Hence, less number of bits were assigned to them. So we can see this paradigm is actually better than the one that we saw before, because we don't have to use fixed size coding now. We are actually using less bits for the characters which are appearing more number of times, and more bits for the characters which are appearing less number of times. Saving a lot amount of memory. So we'll do a little analysis also, how much data we have saved by using this technique. So final size of the message, I mean, you can calculate it afterwards. It will turn out to be 45 bits, and we'll need to send the table, rather either the table or the binary tree along with the unique characters, of course. So we were using 5 unique characters, so that accounts for 40 bits, and the binary codes, the final binary codes which we devised in the last step. So they take up 12 bits. So if we add all of them, it comes out to be 97 bits. So you can see this is actually much better than the algorithm which we were working with before. So original string was of course 160 bits. We have reduced that to 115, and then again to 97. All right. So the next algorithm which I'll be talking about is the limple zip compression, and this algorithm is actually used in your Unix system also. When you you run the command of -zz and zip a file or number of folders. It's a very big family, but one of the algorithms from this family will be encoding your code into some sort of new notation, and then when you decompress it, it will be decoding in this similar fashion. And it is actually very famous algorithm, very ubiquitous algorithm, which is you can find it anywhere. So the idea of this algorithm is the following. So as the input data is being processed, a dictionary is kept. So it doesn't, we won't be working with prefix codes as we were working earlier. We won't be assigning any special codes to our, we'll be doing that, but more importantly, we'll be keeping a dictionary, and that dictionary will be it'll have all sorts of pointers and data locations at which redundancies happen, so that we can refer to it, so that instead of actually storing that number again and again, we can refer to a pointer, and through that we can access that redundant character. So the words are replaced by their corresponding codes, and so is the input file compressed. And the efficiency of the algorithm increases as the number of long and repetitive words in the input data size, they increase. And of course, it's a very big family of algorithms. So as an example, let's say the string is this, that is in front of your screen. This is the, okay. And so I'll be taking over now, telling you how this algorithm works. So we'll be taking two variables, current string and next character, and a dictionary, the current dictionary. So the first input that we see, the data that we see is T. We'll be storing that in the current string, and we'll be checking what is the next character, the immediate next character. It is H. Now we'll be seeing, is TH present in the dictionary or not? If it is not present, then store it. And of course, we'll be assigning some code to this TH also, because at the end we have to encode the data using some, in some encrypted form. We'll be using some special codes. You can either use binary codes or serializing them in the dictionary as they appear. So we'll be continuing this until we find something which is already present in the dictionary. So as you can see, up till IS, up till this term, it will be storing everything as it is in the dictionary, up till SI actually. And then when it encounters an appearance of IS, so it will see that, okay, IS is in dictionary. Now it will not assign a new location for this. Rather, it will say, okay, I'll put a pointer here that will redirect to the dictionary where it is present already. And now will be, the current string will become a subset of it. So this will be stored, and it will be added. The next character will be added. So next character is T. So it becomes IST. It will check if IST is present in the dictionary or not. If it is not, then we'll just store it, and of course add a new code to it. Then we'll continue doing it. If that happens, we'll be resetting the current string, because it doesn't appear in the dictionary. So the next data type that we're appending to the current string has to be a new one. So we'll be resetting it. Now the current string becomes T. We check the next character, TH. It checks that, okay, TH is it's already present in the dictionary. It will set up a pointer to that location, and the algorithm works likewise till the end of the string. So the algorithm which I just discussed with you is one member of the big family of LZ compression algorithm, which is known as LZW, Limpel-Zev-Welch algorithm, if I'm not wrong. Yes, Limpel-Zev-Welch. So it's a very common compression technique, and this algorithm is typically used in GIF and optimally in PDF and TIFF, and it is widely used in Unix file compression utility, as I told you in the beginning only, and best results will be expected with higher redundancy. So apart from simple text reduction, we also have all sorts of methods, techniques to reduce, remove tones and redundant data. And of course, there are algorithms which are lossy in nature, which reduce the size of your audio file, of your video file, or anything of that sort. And they reduce it in such a manner that it is not, the final product is not very different from the original product. So for example, you can see this JPG, it has been compressed to this JPG. And when you do it, your naked eye cannot, oftentimes cannot detect the difference between the original photo and the compressed photo. So it is actually a very magnified view of 8 pixel by 8 pixel, I guess. Yeah, 8 pixel by 8 pixel portion of that image, and then it has been, reduced to something very simple, so as to compress down the string in the image. And likewise, we have also one more algorithm which I won't be discussing in this presentation, which is arithmetic coding. So it's actually a very interesting algorithm which converts a total string, or you can also have a very big string, a whole document full of it, and it converts that to a single floating point number. And uh, the good thing about that algorithm is the compression ratio. It's often very high as compared to Hoffman coding or simple prefix coding. If you are interested, then you can also always Google it up, and it's actually a very nice algorithm and the way it works. So more fancy video compressors approximate redundant frames and copy a frame from last second rather than using a new frame. This is known as temporal redundancy. And if you're watching this screen share right now, there's a very high chance, high probability that you're seeing the slides of the past, because it is being, dynamically encoded and then decoded at your end. And um, there are many fancy algorithms which try to approximate how frames are occurring. So rather than assigning a new frame to a new memory location, what they do is, if it is not, there is not much changes in the frames, they use the previous one only to be used in the present. And as a common standard, MPEG4 videos, they're often 20 to 200 times smaller than the original file. So that sums up my presentation. And yeah, if you already know about these algorithms and all these techniques, so I hope it was a pleasant revision for you. And yeah, that's it.
Thanks, Ashwani. This was really nice. Thank you.
Hello. Uh, do I go next?
Yeah.
Yeah, I
कोई
think
questions नहीं है
you
तो
are
I think
next in the
go
line.
ahead. Yeah, I think it's Atharva itself in the list. Atharva के बाद Anku.
Hello. Am I visible?
Yeah.
Yeah, the screen.
And audio?
हाँ सही है.
I'm Atharva, and I'll be talking about the Unix philosophy, something very simple. Uh, so the Unix philosophy, going back in 1960s, uh, why Unix philosophy, why Unix was made. There were in 1940s, 50s, every operating system were very machine specific. So uh, like we needed a different operating system on a different machine. So Unix guys wanted to make a base operating system that would be installed on all machines and be extended and have an extended support for all the machines that would be made in future. So that is why it was made. And during this, one amazing language came into existence, and that was C. Like they initially started with B. It they wanted to transfer to a more viable language than a machine language, as it was very difficult to code in that. So they started with B, and then in the process they made new B. As there were many glitches, they finally came up with C, and C was made only uh, keeping Unix in mind, and it only had features that Unix needed. I'll share the link if anyone wants to read more about this. So coming back to the Unix philosophy, so Now, one of the I've sh- brought them down to four basic things. The first is pipeline. The entire Unix system is based on pipes, one command being the input for the other. One command might look as an output for you, but it should be created in such a way that it is an input for some other command. uh, if you have played with terminal, you know these three things. The first is fortune. It shows some random quotes, like a cow says, cow saying something, and a lolcat gives rainbow color to the text we add. Now, if we pipe all these three commands together, we would get something like this. So this is how the entire Unix system is. Like, everything is piped with something else, so that and that is how it works. Like, everything as a file. Now this is some other command called as pony say. Uh, Pony say thinking about cow saying something else. So this is how amazing Unix is, and that is how it was built. Now, Unix shortens everything down to everything is a file. Right from the directory, the hardware resources, devices, and processes, everything is a file in Unix based systems. Uh, Also, the shared memory, the memory that is shared between one program to the other, is also a file. Uh, and I have given a screenshot of my terminal. In this, as you can see, the processes we run that also act as files. They are dynamic. They keep changing very rapidly. Even the devices that we have uh, uh, can be shortened down to files, and we can see them in our directory called as DEV. Uh, the next is connected programs. Uh, we can compare this with the Lego analogy. Uh, Basically, uh, every program doing one thing well, rather than making one program do 10 different tasks. Unix expects us to write a simple code that such that one program doing one thing well, and then we can easily debug if there are any errors in the operating system. Uh, if you see any error, uh, it is very easy to sort it down, because we know everything is in a lot of pieces, and we just have to replace that particular piece uh, that is giving problem. This can be compared with the Lego analogy. No matter how complex your Lego house is, uh, it is you can always replace one particular block that is causing problems, or if some better block is available. So that is why Unix systems are highly customizable, and that has given people do make amazing systems. Like, we can see stuff on Unix spawn and stuff. uh, they make a beautiful system using these uh, the programs that use these analogies. So thinking if we boil all these rules that Unix has given, everything is a file and everything running is a process. Everything that we do can be seen in slash proc. We can do you can change your directory, and uh, you can see all the processes, or use something like gtop or htop for the same. Then everything is in text or data file. Every device that we use is a file, and that can be opened in a text or data format. And yeah, then talking about Emacs, Unix philosophy states doing one thing well, and we also have programs that can do everything but cannot do anything well. Emacs is an entire operating system, but it doesn't do anything well. So anyways, we can also use those programs and make memes of them. And shell is everything. In Linux, the piping system works so amazing that we don't need a GUI. So we uh, we are uh, we can do anything in terminal. So let's discuss some rules. I won't take a lot of time. I would just discuss some of them. Modularity, it asks us to keep simple connected programs with clean interface. Clarity says clarity greater than cleverness. We want one program to be written such that anyone else who comes be able to see that program and uh, and be able to interpret it. That is the reason why Linux has been able to there have been more than 10,000 contributors to Linux system, and uh, like it has grown so much since years now. Talking about composition, it's being able to connect to others, one program being able to connect to the other. uh, Separation, separate interface from engine. We don't want our program to be much connected with the hardware. It should be separate. Then simplicity, design for simplicity and use complexity when needed. Unix philosophy isn't against algorithms. Use it, but they say use it only when needed. Then transparency, easy to debug and inspect. Then generation, write programs that can write programs when possible, like programs that would write program for you. This is one thing that was that makes Unix systems unique. uh, and then optimization, uh, getting it working before optimizing it. First see if your code works and only then optimize it. And then comes extensibility, that is future is sooner than you think it is. So design for the future. Your software should be extensible to for newer abilities and being able to connect with others. So boiling it more, it would come to one simple line, that is keep it simple stupid. So that is the entire Unix philosophy. Yeah, that's it from my side.
By the way, which terminal is that? Like ZSH or Fish?
G shell.
Okay, can you send me the dot files?
Yeah, yeah, they are on GitHub actually. Wait.
Okay, nice.
It's a nice talk. Really enjoyed it. So, um, are there any questions?
People were demanding Atharva to show his terminal and rising.
Oh, okay.
Bro, fans are requesting Atharva.
Oh, I don't know if you're able to see वो दो screen है ना एक से. Uh, so uh,
Which
yeah,
terminal is that? Is it Alacrity?
yeah, it is Alacrity.
I recently switched to Kitty. because it has tabs.
Yeah,
Same.
I think Tmux plus Alacrity works well for me
yeah. There
because
is also like a terminal written in Rust. It's in development process. Like
Western is the word?
Why
This
is everything being written in Rust again?
yeah,
Unix philosophy, right once.
yeah. Rust is also being implemented in Linux kernel now. Very soon.
Yes.
They have made modules on like
ये Gentoo है ना? So you don't use
नहीं
system
नहीं
D, right?
ये आर्च है अभी तो मतलब उसमें मैं कस्टम कर्नल में वो डालना भूल गया माइक्रोफोन तो वापस बिल्ड करना पड़ेगा
Right.
वैसे कितना टाइम लगा था बिल्ड होने में?
वो मैं गाँव गया था ना 7 दिन तो 7 दिन में
नाइस नाइस.
वो सुबह सुबह लगा के जाते थे वो शाम शाम तक कंपाइल ही होता था तो
काफी सही. Next talk पे जाएं? Yash, I think you're next.
No, please, sir. All right. I hope my screen is visible. Yeah. So, yeah, it's visible, right? I don't know if the keynote window works.
Yep.
Okay. So, hi. I'll be talking about something that is really far, far, far from anything tech. So just brace yourselves. It's because the stage for the talk so far has been technical, 99% of it. So yeah, just a brief over it, and I'll be talking about the Bhagavad Gita, of course. And yeah, I know it was taken up before. It was taken up by Likit, but you gotta admit that you can never have enough of the Bhagavad Gita talks. So yeah, let's just dive right into it. I'm just kidding. I just wanted to trigger Rakar over this. Anyway, so what will I be talking about actually? I'll just show you a meme, and I think you can figure it out. So this is your average 17th century meme by an artist called Rembrandt, who's a very famous artist from the 17th century. So it's a philosopher in meditation. But I guess most of the people, I think all of the people here, none of them were alive in the 17th century. So I'll just give you a 21st century meme. So why do I exist? So just imagine yourself after the incense, sitting in the balcony, sipping up a cup of coffee, and just think about randomly what is the meaning of life, what is it all about, who are we, and why are we here? Are there any goals? Is there any end to it? Like, and what is the reason to live? Is there any achievement unlocked kind of thing that is waiting for me, or why am I even having all of this stuff done? And most of the people, when they come across these thoughts, they just go, let's just open Discord and chill. Why do I even have to care about this stuff? And I didn't. I spend most of my time. I'm kind of a philosophy nerd, so I spend most of my time exploring this question and really looking into perspectives that many great thinkers have gone through. And I came across two interesting places in the medieval era or the ancient times. And there are many interesting theories, but uh, due to the restrictions over the time, I'll just stick to two. And the first one is, I think you might have guessed it by now, ancient Greece. It's just old, long, bearded dudes, and they really like thinking. Love thinking. So, what did they think about? These are the two famous ones that I'll be talking about today. The one on the right is Plato, and the one left is Aristotle. So let's start with Plato. So Plato came up with this idea of Platonism. It's pretty obvious from the name, and he came up with this theory of forms. So, what are these forms? Forms are metaphysical beings known as the heavenly forms. So, it is not something that you can physically achieve, but it is something that you can emotionally achieve. And you can really think of these as the achievements or the things that you need to do in your life to finally, be meaningful, live a meaningful life kind of thing. So, you can compare it with the coins in our favorite game, Mario. So, these are things you need to collect before you go to the final level. And the goal is to attain the final form of good, or the final form, which is the highest good. And that is basically an achievement chart. So you complete this, and it all lead to a meaningful life if you achieve the final good. And the final good is the end of the game. But I wasn't really satisfied with this theory because it didn't tell what the good was. It didn't define it in proper ways, and it didn't tell me what are the intermediate goods that I need to achieve to live a meaningful life. So I went to his buddy, Aristotle, and this is a pretty difficult word to pronounce, and I don't know if I'm doing it right, but I basically say Aristotelianism, and I don't know if it's the right way, but it is what it is. He defined what being virtuous meant, what a human must do uh, to be called virtuous, and it's a very nerdy definition, so we won't go over it. It's not that elegant, so I just skipped it. But it is a pretty good definition. So the achievements, what he said was the achievements are cyclic. You do a stuff A to achieve something that is point B, and then you go to point C. And for doing point D, you need to complete point C. So basically, you're doing JE to get into the IIT. Why do you want to get into the IIT? Because you like engineering. Why do you like engineering? At a point, you can't really answer these questions. So it's called an infinite regression. That's what he called it. And what he proposed was there is a final destination that is called the highest good, pretty similar to Plato, what Plato said, but the highest good is desirable for its own sake. You don't achieve the highest good, in with the mindset that okay, if I do this, I can get to this. No, that's the final, the finito. So, aka happiness. That is what is termed as happiness. Everything you do will or should lead to this final level, and that is how Aristotle said you lead a meaningful life. So, what is this highest good? Defining happiness. Well, not really. So, what he said, what these are the exact words, I think translated from Greek, obviously. So, what is the highest good in all matters of action? To the name, there is an almost complete agreement for the uneducated and educated alike to call it happiness. I think most of us agree. The final destination must be happiness for all of us, right? And make happiness identical with the good life and successful living. Now, this is a debated point that being successful and being happy are two different things, and it's a whole new debate. And let's not get into it. But the final line is where the catch comes in. They disagree, however, about the meaning of happiness. So people don't really agree what happiness means. They know, okay, I want to do this to be happy, but what is happiness? And that is what he points out, that no one agrees on the meaning of happiness. For every different person, it's different. And this pretty much sums up Western philosophies over ancient Western philosophies over the meaning of life. But there are some more. Epicureanism is basically mortal soul, nothing mysterious about it. There's a soul, and your body and your soul are the same thing. So you need to do everything you want to do in the same life. There's no afterlife and all bullshit like that. So everything you need to do, just do it right now, is what they say. Stoicism is again really famous, and it is kind of obvious, free from suffering. He didn't define what suffering was, or neither do his followers do, but that is their ideology. Anything, any action you do is to be free from suffering, to be as far as possible from suffering. Nihilism is pretty interesting. It came up in the Enlightenment era, not really the ancient Greek philosophy. So nothing matters. It's all meaningless. The point you come to, you sit in a balcony and you be like, what is the meaning of life? It shouldn't matter to you. One of the quotes is, when you start thinking about the meaning of life, you stop living life, and that is pretty good. But then that doesn't fit with me. I really need to know what the the mechanics of all of it is. And nihilism is very popular again. Existentialism is everyone creates their own meaning of life, so there's no point in discussing all of this. Everyone has their own personal meaning of life, and this is inbred in most of the philosophy we will discuss today. So that is with one place, Greece. What is the other place? The second place is South Asia, mainly India. And India had this philosophy about meaning of life very much connected to religion. Now there are Western religions which define it too, but I don't know a lot about it. And mainly India is mainly Hinduism. So Hindu philosophies. Please spare me. I'm not talking about the religion. I'm just talking about a way of life. So yeah, let's not the religion, but yes, they are pretty close. We the Hindus do follow the Hindu philosophies and try to keep up with it. So yeah, let's dive right into it. So I started with this question: what is the goal of life? Well, Hindu philosophy say there's not one, there's actually four. There's four ways of living your life. So the first one is karma, and these are all in the increasing order of niceness. Basically, if you achieve the first one, you should look for the second one. So karma, that is living just for your desire, pleasure, and wish. And there's artha, that is living for power, wealth, and glory, and being famous. That is your entire goal. Dharma, that is your duty, and this is where ahimsa and all of the philosophies come in. That you need your karma is your main determiner. That is what you do in life that defines the meaning of life, and you need to do good. Good isn't defined again, but anything morally good is good. So, and the best way of living life is moksha, which is pretty religious, I guess. So I'm not really that interested in it. But moksha is basically liberation from pain or samsara. Samsara is this universe where we'll all put into, and it's just suffering, is what it says. So these are the Hindu philosophies, and what the pillars are behind it is do good, be nice, be welcoming, and all of the philosophies that we have been following from our childhood. So yeah, and there is one theory that really stands out. It's not really a theory, and to keep this talk kind of small, I just included these two, and this is my personal favorite. So it's a short story, The Egg by Andy Weir. You must have heard of Andy's work, The Martian, which is pretty famous. Even the movie came out. So yeah, this is a short story, not really a theory, but an interesting way of looking at the universe. So, not spoiling the plot for anyone who hasn't read it yet. It's a must read. Really recommend it. So, the plot in its basic form is a man dies, and he finds out that every other person that is living in the living on Earth right now or anywhere in the universe is his own reincarnation. So anything that has happened in the past, any person from Hitler to Gandhi to anyone, or anyone who will be born in the future, is his own incarnation. So doing any kind of act to any person is done on yourself. Is done on yourself. It should be not one yourself. I'm so sorry. So whatever you're doing, if it's a good act or a bad act or any kind of thing you're dealing with any person, you're dealing with your own self. And the point of all of this is, why do we do this? For you to mature and attain godhood. Now, I'm not really interested in the godhood kind of thing, but the main philosophy from this, what I derive is, it's a work of fiction, so you don't really have to take it literally. But the philosophy behind this is, it merges the concepts of selflessness and selfishness. So, what is selfishness? Working for your own good, right? And what is selflessness? Working for someone else's good. You're doing your work that will benefit someone else. But who is the someone else? According to the theory, the someone else is you itself. So it really blends all of this concepts into one. So if you're working for someone else, take it as a selfish act, do it for yourself, and be nice to everyone, is what the summary is. And it's a famous YouTube channel called Quetzalcoatl, and he made a video over the 10-year anniversary of the book, and it's a must watch. I've linked the video in the slide, and if you have like 7 minutes, you can go and watch it. So yeah, that should pretty much conclude over the starting points of the philosophical way. There's a lot of theories and there's a lot of ways of looking at it. And if you find anything interesting, please consider DMing me. And there's an interesting clip I want to show to sum it all up, whatever I've told by now. So that should be right here. Okay, anyway, so this is my quote. Life is just an elaborate ritual. So, yeah, you've all been successfully recruited. And let's not take this as the point of the presentation. The point of the presentation is thinking about the meaning of life and really not ignoring it. But yeah, that was a good recruit. Thank you.
Thanks. Yes, that was quite interesting. The recall was unnecessary.
I just want
We're right. Yeah, काफी interesting.
ब्रो तुम कुछ गए या कुछ भी सिसिफस एक्जिबर वो सब फॉलो ज्यादा देखते हो?
How is it pronounced firstly? मेरे को अब आज पता लगा it has a weird pronunciation.
प्रोनाउंसिएशन छोड़ो.
कुछ के साथ
गुड्स के साथ मैंने बहुत प्रैक्टिस किया था.
Like in German it is like shortly said, मतलब said in like brief.
गुड्स के साथ.
I always thought it was with the Kurtz.
the German word is that's why.
मुझे बहुत
हाँ बोलो.
ये प्रोनाउंसिएशन सीखने, आई मीन स्पेलिंग सीखने में मुझे शायद 1 महीना लगा था गुड्स के साथ का.
यस, तुमने like कुछ बुक्स पढ़े हैं क्या? Like have you read Camus और Schopenhauer?
12th में stoicism में बहुत इंटरेस्ट है, so I read the Stoics and really मतलब बहुत vague रहते हैं ये सारी चीजें, but it really gives you your own theory. Kind of interesting.
Right. मेरा भी like एडिक्शन चल रहा था काफी कुछ महीनों तक, like मैं पूरा घुस गया था इस सब में. Like recently I read Nietzsche and like that was that's pretty much like a conclusion to it. Okay, बहुत mind blowing philosophy है Nietzsche.
I started with scientific methods, like biology defines life to be anything, meaning of life to be anything that achieves negative entropy. So you try to bring order within yourself. That is a living being, but that doesn't really give you a satisfying meaning. So that is where I turned to philosophy.
Nice. एक चैनल है द एकेडमी ऑफ आइडियाज करके, उनका काफी इंटरेस्टिंग है चैनल. लाइक इट्स वेरी इंफॉर्मेटिव.
Shall I go next?
Yeah.
Hello everyone. Is my screen visible?
Yep.
Yeah. So actually, for today's lightning talk presentation, I'd not be exactly talking about some coding tech or some form of knowledge that I would give you. I would just give you a trivia about what are the upcoming innovations and what are our challenges to the current computing system that we have today. So to set a background, I'd compare the current computing system, say what a personal computing system, to the most common form of intelligence that we know, that is our brain. And I would make these comparisons based on 4 parameters. There would be, and I would be talking about all of them in brief, so that I could lay more than foundations. So, talking about the first parameter, storage. We all know actually over this lightning talk only about 3 to 4 times we have known that how does a computer stores information. It like every form of information, it converts into a combination of just 2 digits, 0 and 1, and it stores it. So if we talk about the amount of information that a personal computing system has, it might be 1 to 2 TB of hard drives or SSDs, and uh, but when I talk about the brain, it doesn't stores information in binary encoding. It has millions and billions of neurons, and each neuron has some form of information. Like whenever there is a thought processed or whenever action is required, each neuron gets a spark, and that lights up the neuron, and that part of the brain sends action to your body, and your body acts as an actuator to respond to this situation. Now, talking about how much of this information or how much of information neurons can store as compared to computers, uh, brain can store information. This might be surprising, but in the order of petabytes, which is about a billion gigabytes, or you could say about thousands of SSDs, 1 TB SSDs that your PCs may have. So there's no point in discussing further that brain can, of course, store more data than a personal computing system that we have today. So I'll be moving to the next point, the processing speed. The picture for this might be clear to all of us, but I'll talk about some general facts to make it more clear. About computers, we know that what processing speeds do we have, but brains cannot process about more information than 60 bits in a second. uh, Talking about time, suppose you want to complete a thought about going to a place, thought about lifting an object, it takes about 100 to 250 milliseconds. uh, Actually, 100 to 250 milliseconds is like pretty good. But if you talk about normal situations, it might go above that also. So if we talk about the fastest responses of brain also, then it takes about 100 to 250 seconds. And if I compute the frequency speed using this, it would be around 4 to 10 hertz. And we know that our computer processing speed is order of gigahertz, 2 to 4 gigahertz, which is exponentially very much compared to brain. So, of course, absolute winner here is computer. Now, talking about energy efficiency, a typical computer, or say your personal computer on your desk, consumes lot of power, like about 100 watts of power, and your brain typically is 10 times more efficient than this. And here you can see in the image, there's a graph, and here's the energy consumption. It's in kilowatt hour unit, and kilowatt per year, your computer consumes over 200 kilowatt per hour, kilowatt hour units of energy. Now, brain is like 10 times more efficient than this. And in fact, the bulb which might be inside your room is consumes more power than it. It might be of 15 to 12 watts or 20 watts. Brain consumes about 10 watts. So I think the advertisement of Mentos is quite relevant here, that don't need much of cost to run your or light your brain. So of course, energy efficiency, brain wins this contest. And talking about memory, now this is the point where the picture becomes unclear. It is about what type of memory. Now, talking about what type of memory, I would say that suppose if I know an answer to a question in an examination, I've studied the question from a book, and if computer has also that book, it knows that information, I can forget that information, and computer will definitely access that information and give the answer. So memory access is definitely better in like that type of memory access is definitely better in computer. But suppose I want to characterize some part of memory. So computers can't classify memory. all types of data on a computer are of equal priority. Like any type of data you start searching in your computer, it would start from the beginning and it would stop at the point where it finds that data. And talking about your brain, it may classify that information. In one of the images that I showed back, I showed that there are different parts of brain that store different types of information. And I'll show that image again. I'd say that if you want to access some information, like if you want to access some memory of your childhood, maybe you would access it faster than your computer, because that is a classified memory. Like you have a priority order for that, a good memory, but computer doesn't. Somewhat you can say the IQ of computer is zero. Like it doesn't have any intelligence. It just performs a set of instructions that I or you give it. Uh, I think these 4 points make the conclusion pretty clear that our computing system, though exponentially fast, but it still doesn't completely outweigh the brain. But actually, we are not here to replace our computers with our brain. We are here to make them work at par with our brains. So let's look at some of the upcoming innovations that might change the course of computing systems that we have today. These might sound somewhat ideological or theoretical, but I picked the only ones where there is some progress. So, firstly, I'd start from the basic hardware part, that is graphene-based transistor. Uh, we know that a silicon-based transistor has a life. It gets weird and like tiered by time, and it's like it has physical boundaries of design and also durability. So we can replace it. We are in that process. There is not too much progress in that, but I think I read an article where it said that a MIT team in 2019 they made a graphene based transistor and that did some simple job, and just it was a simple job, but it did it with like pretty energy efficiency, and like it was quite faster. Next, I would talk about quantum computing, and it is like the most one of the most awaited computing system. We are not quite far uh, reaching it because of its physical limitations. Like there are too much, as you can see in this image, there are too much limitations to store these types of computer. They are too physical disturbance creates a lot of noise in them, so noise errors in them. And I read something that they need to be stored in absolute zero temperature, and I think these qubits are stored in vacuum. Now talking about qubits, I should tell you what are the basis of quantum computing. So as we know, binary encoding, any type of computer like supercomputer, any supercomputer that we know or that is coming, uh, is gonna still represent each data as a combination of two binary digits, 0 and 1. Whereas our quantum supremacy says that every data can be has uncertainty, and it can be represented as superposition of the two quantum two bits, 0 and 1. Like you can say it like alpha times 1 plus beta times 0. So it can be 1 and 0 at the same times, plus it can be any value in between them. So this is where uncertainty comes. I might not be quite clear to you, but I can explain in simple terms. Suppose you are in a maze, and like a normal computing system, it would start, I'm just explaining for an example, it would start a for loop, it would try all the combinations of path, and wherever it reaches a dead end, it would start from beginning. What would a quantum computer? Quantum computer, like recursion, what it does is that it dynamically starts, and there are like many bifurcations of path going in that maze, and wherever it reaches dead end, it tries to go back or start from the place that was before it and there was no dead end, and then it chooses next path. So in this way, quantum computer, if designed and if developed properly, could be exponentially faster than any supercomputer or best computers we have. Like you can see in this figure, there is a exponential conversion of qubits, the bits of quantum computers. Like 3 bits stands for 8 classical bits. That means that you can see alpha and beta, it can be any value. So each bit of quantum computer is representing 2 bits. So like exponentially, each qubit grows into a classical bits, and till now, I think I read that by today we have a quantum computer of size 50 qubits, and in fact, you can try some quantum computers from your IBM has a website for that. I don't exactly remember, but I'll find and post the link. Next, I'll not delay much. Next, I'll talk. Be talking about DNA data storage. I talked about this in one of the previous slide. Actually, I didn't talk about it. Sorry, I wrote it in the slide and forgot to mention it. That we are facing problem of data storage. You all know that the pen drive or hard disk that we have may be like weird by time, and it may not last forever, and also we are out of storage devices, like so what we are now moving towards, and like many big brands are into this, Microsoft and others, they are into the research for DNA data storage. You all know that binary code can be converted to hexadecimal code. So similarly, you can convert the binary code into bases of 4, like combine 2 bits at a time and convert it into one nucleic acid, and you can store data. And actually, there is some advancement in it, and it might not be far then that we would see DNA data storage devices. Of course, you would not like it that someone would take your DNA and store data on it, but it's quite efficient. For example, like here I have mentioned that uh, a genome of K beer that died 3 lakh years ago, DNA based data was stored in its genome, and like it lasted still. Like DNA, of course, is more stable than physical form of data storage system that we have. Moving forward, now in these lightning talks also, some of my friends have mentioned about neural networks and all that, a technique to uh, gain intelligence just like brain. So talking about it, uh, there's something called neuromorphic technology. The goal of this is to create a computing system that tries to replicate human level of intelligence, and might be someday it may represent, it could copy your cognition power, or it could make decisions for you that still neural networks or present form of AI couldn't do. I think this system is the best way to grow in AI, because we all know that currently we have the most high intelligence quotient in all breeds of uh, species available, and our intelligent quotient and cognition power, none of the computers could still follow. But if we try to replicate a computing system via brain, and I already told earlier that how does human brain work, that neurons are connected. Whenever a thought or a response action is triggered, each neurons get a synapses, they spark and they connect to each other, and then a action is provided to you to perform. Similarly, a computing system can be created. This image is not clear, but what I could understand is that, uh, see, the computing system hardware is like a neural network. Anytime, there's some action, only that part of transistor is lighted, which consists of that neuron. You would say neuron in that like computer language. Next, I'll talk about optical computing. We all know that photons are much lighter than electrons. So, in any transistor, do you know that how power is generated? The electrons are excited, and then the energy is transferred. So, what we can do is that the photons are pretty lightweight than compared to electrons, so they could be excited easier. So we could build computing system based on optical transistors. Now, how do we obtain an optical transistor? We do it by using non-linear refractive indices material, and as similar to a normal transistor on or off stage, whenever there's light into it, you may get the 1 bit, and whenever there's no light, you may get the 0 bit, just like digital signal. And also, this might be fast because of the light reflective technology that could be bought into it. And it is estimated that optical computing at nano scale would be possible at literal speed of light, would some would had something at par processes with light. And it's just not completely developed, but we are not far ahead of it. We are making some progress in this. uh, this is I think most of you might know about it, distributed computing. It's developed, and uh, it's not far. Actually, we have that system. And you might all have heard about folding at the rate home. It's an organization which you can join. And what a distributed computing system is that all the jobs are divided into piecewise operations, and they are distributed into many computers. And all the computers, like if I have to perform a plus b, I'll calculate a, you will calculate b, we would submit to the server would store a plus b. So that's what a distributed computing system is in short. So this organization, folding at the rate home, what is it's that is invites people, or you can volunteer there, you can join, you can stimulate protein molecules. And currently it's more towards targeted more towards COVID-19, but it is expected, like it's targeting to find a cure to diseases like Alzheimer, cancer, etc. And I think currently, might not be in 1 or 2 years, but currently it is one of the most fastest form of computing system, because it can perform about as mentioned 1.5 exaflops of power. like that is ability to perform quintillion calculations per second. These are far beyond the present supercomputing systems we have now. But it is projected that the computing system that would be coming a captain in future 2023 would be faster than it. But presently it is one of the most fastest computing system, and it should be. Like you all know, divide and conquer is one of the best method in any task you perform in your daily life. So that's all. Thank you. I expect I am much have not taken too long.
Yeah, it was nice. Like, how did you get to know all of this? How did you do a survey or do you regularly follow this feed?
No, actually, I saw a video on this, like on YouTube feed on Wired quantum computing, and like
Uh,
basically I was going to say about quantum computing, but I thought that since I should lay a background, so I did everything in brief.
nice. That wired वाला वो वाला क्या कि explaining quantum computing to fight 5 levels.
हाँ हाँ हाँ.
Uh,
And like this is the technology, I think this is the only technology where all the companies openly write on their website about the progress, because like they could make like too much profit from it if it's developed. Like Intel has a full uh, page on it, like about all its progresses that it has done. And I also went today only. I went to a website of IBM where I could play like that with that quantum computers, their quantum computers.
did you try those challenges, Qiskit challenges that happen every year? I think twice a year, not sure the frequency. Try them. Those are from IBM only. They are also like interesting. You can try them.
Okay, thank you.
Shall I go next then?
Yeah.
Okay. Okay. So, hello everyone. We all have heard about IoT, but like recently, this new acronym created a buzz everywhere. IOB, that's Internet of Behaviors. So, let's talk tonight about that. So, first of all, what is IoT? IOB. So, IOB extends from IoT, Internet of Things. As we all know, that IoT is constantly expanding and evolving. So, like data collection from these objects provide really valuable information about users' behavior. Hence, the IOB attempts to understand the data collected from the user's online activity from basically behavioral psychology perspective. It focuses on how to understand the data and how to apply that understanding to create and market new products, all from human psychology perspective. So that's IOB technology and analyzing data plus behavioral science. So next is like, what is the purpose of it? So basic purpose of it is to capture, analyze, understand and respond to all types of human behaviors, and then track and interpret those behaviors with the help of certain learning algorithms or CV. And these information is collected on all facets of users life, so with the help of just like improving customer services and quality and efficiency of their products. So with the result of this analysis, it informs new approaches, designing a user experience, search experience optimization, and how to market the end products and services offered by companies. Next is like, what does the what value IOB gives. So seen from an industrial point of view, it analyzes customers' buying habits across all platforms, and then study previously unattainable data on how users interact with devices and products, obtain more detailed information about where a customer is buying in the process, so that it can keep track of it, and then provide real-time POS, that's point of sale notification and targeting, and then resolves problem quickly to close sales and keep customers happy. So this all we see what values IOB can add, and few are these are some like use cases which have been evolved around it. So like during the pandemic in hospitalization industry, so computer vision was used to recognize whether person was wearing mask or not. Some thermal imagers were used to identify with people with increased body temperature, and even Uber uses IoT data to analyze its audience preferences and find new approach to customers. And in 2018, the facial recognition system was successfully integrated into the development of directrix barista for coffee houses, and as a result the product determines the sex, age and mood. It analyzes the result and offers the client an appropriate drink. This all we see about purpose and its use cases of IoB, but there's some like real ethical problems. So the problem that can occur with this technology is not of technical nature. The IoB is like up against for challenge of how data is collected, stored and used. Its level of access is difficult to control, and the companies like Google, Facebook, Amazon continues to acquire software that potentially brings the user from a single app to their entire online ecosystem. So this basically presents significant legal and security risk to privacy issues. And not only that, this behavioral data can allow cyber criminals to access sensitive data that reveals human patterns, access codes, and even bank codes. So yeah, that's why it's important to have a secure platform for storage and execution of codes data with the use of encryption tools. So that's for it. Thank you.
Hello.
Hello. Yeah.
So IoT is just IoT applying for behaviors.
Yeah, basically, like IoT collects data and IoP is analyzing the data and all of the MLL, all the things which is used to make patterns out of data and all of that from.
Where can I read more about this? Like, from how did you get it? Like, sounds interesting.
So recently I was looking for IoT. That's where it came up, like first Gartner and his theories, and like on YouTube also. It's there is many thing about this, and I'll send you the links also about this on net.
Cool, cool. Thanks. We can talk with. We can start with next one.
Okay, so can I share?
Mm-hmm.
Okay. Okay, is it visible? Okay. So the topic of my presentation for my lightning talk today is science of fear in humans. It's basically a brief dive into the functioning of brain with respect to the fear stimulus. So what makes a thing actually scary? So when I prepared this presentation, I simply searched the word scary on Google just straight away. And quite unsurprisingly, the results were well scary. So what is something between? What is something common between these images? Well, is it the fact that they are creepy, or perhaps haunting and abnormal? Well, as it turns out, it's a lot of things, and not they're like quite similar and different at the same time. So, how is fear perceived by the human, by the brain? So through evolution, we have trained our brains to be afraid of potentially dangerous things, like perhaps a lion or maybe a snake, because through the process of evolution, those who were afraid of these entities ran away from them, of course, and were more likely to pass on their genes to the next generation of their species. That's just how evolution works, and being afraid is rewarded with survivability in the species, and thus it's not uncommon to observe a fear response, also known as the state of being afraid in human beings or any other complex life form for that matter. So, biological reasons for fear. It is a threat stimulus, such as the sight of a predator, triggers a fear response in the amygdala, which is located at the center of the brain, which activates areas involved in preparation of motor functions involved in fight or flight. It also triggers the release of stress hormones and sympathetic nervous system. So that's how. So this is how the external stimuli actually affects our brain, and that's how we perceive fear. Fear can be learned subconsciously. So similar to obedience training in dogs, which is quite a present process. When your pet does something desirable, you treat them with treats, which trains their brain to do that thing again. As for the humans, it's not quite as pleasant. So deliberately learned pain. In this process, a human being is subjected to pain by giving an external stimulus, such as being shown a relatively normal image, such as a simple scenery. And whenever that scenery is shown to that person, he is subjected to extreme amounts of pain. And this trains his brain to perceive fear using that apparently non-dangerous picture of a scenery. Now, fear can also be vicarious pain, vicariously perceived pain, which is basically watching others feel pain, and as a process, you are afraid of that. It's basically second-hand pain. Now, fear is mostly inherited. The life form doesn't have to be intelligent like human beings to be afraid. Even a newborn baby can be distressed by various factors. These factors are called innate aversions. This feeling of distress is psychologically painful and causes psychologically painful and causes pyroerection reflex, which is also called which is also called fission, which is nothing but goosebumps. Uh, so that thus we learn to be afraid of feeling these reflexes, and it's not actually the pain that we fear; it's the perception of an impending pain that what causes the fear, and that's how we feel fear. Now, human brain has a lot of innate aversions. You can think of them like nodes, similar to ones on a machine learning model, perhaps, in that sense that all of them lead to a common link. Yet each holds a different weight, which varies from person to person. The common link here is death. So each innate aversion inevitably and eventually leads to the fear of dying. Because, of course, that's the point of evolution, that's the point of survival, to avoid death. There are a few well known innate aversions. The first one is pain. So, such stimulus, such as perhaps fire, an electric shock, wild animals, these so these do these external stimulus are what excuse me what I'm sorry for that. So these external stimulus, such as fire, electric shock, or perhaps even wild animals, are what causes to fear pain. But of course, that's not same for every human being. Some people don't perceive pain as much as the others. So thus how it's differently weighed among different human beings. Second is isolation. So perhaps when you're in a closed room, such people like who are claustrophobic, or perhaps stranded on an empty island. But then again, it's not the same for every person, such as hermits, people who actually enjoy isolation and actually love it. The next one is the unknown or the abnormal. So this innate aversion is basically things that are creepy in general, which we cannot explain, such as like darkness or perhaps ghosts. Now, next are not excuse me. The next innate aversions are disease, sudden movement, which actually triggers our fight and flight sensation in our bodies, which a lot of crappy horror movies actually depend on sudden movement, which also be called jump scares. Next, suffocation, which also just in general just uh, limiting the amount of oxygen that reaches your brain, which causes the sensation of drowning. And falling, such as when we are now next one is falling. So when our ancestor used to be monkeys, of course, so they used to live on trees, and falling was actually then that time when if they suppose they were sleeping and they actually fell from the tree, they could actually risk dying, and those who actually developed a fear response from falling actually survived, and that's why we have a falling response in our brain. And the last one is incapacitation, which is the feeling of not being able to do what you want to do, such as the inability to move or basic paralysis, uh, even sleep paralysis that some people experience when they are actually unable to move when they are perhaps in a dark room or some dark figure looks down upon them. So, what makes when I began my presentation, I showed you some pictures. So, what makes these things scary? To be specific, what innate aversion makes these pictures scary? So, starting from the right hand side, this is Annabelle. This is actually the one of the most creepiest thing in my experience, and I absolutely hate it. So the innate aversion that it causes in my brain is the unknown or the abnormal, simply the quality of being creepy in general. The next painting is a picture of a man that's screaming whose face is disproportional. It's also unknown and abnormal as compared to normal human beings, and thus it's creepy. The third picture is actually not that scary because it's just a simple scenery. So what's actually causing so what depends here actually is the context. This painting is no ordinary painting. It was painted by Adolf Hitler when he was a painter, and that this painting then triggers the pain innate aversion, which actually makes us fear of this painting. So without context, it's actually not at all fearful. But when we are given the context, it just suddenly changes the context. And that's it for my presentation. Thank you so much. If you have any question, so I can answer them.
Nice. That was quite interesting. Have you heard of the Little Albert experiment?
Which one?
There's an experiment called Little Albert experiment.
I
So
actually have not heard of it.
yeah, so like it was a highly unethical experiment where they sort of tried creating a phobia in a kid for like animals, and so what they did was they basically put furry animals, and whenever the child tried to touch that, they like played a very unpleasant sound. So the child later
Yeah.
had a fear of everything that was furry. So for animals and stuff like that. So
That's actually learned. That's actually how we learn fear subconsciously.
yeah.
Deliberately not playing, of course.
Right. Yeah.
अरे थोड़ा आउट ऑफ कंटेक्स्ट बट क्योंकि बात में अनएथिकल एक्सपेरिमेंट्स लाइक टॉपिक ब्रिंग किया तो और स्टैनफोर्ड प्रिजन एक्सपेरिमेंट पता है क्या?
Yes, I have actually.
हाँ वो नेक्स्ट लेवल
super unethical.
हाँ
हाँ हाँ
It's
राइट
actually
राइट राइट लाइक स्टूडेंट्स को बोला
it's
ना
actually one of my favorite like
कौन सा कौन सा
history.
कौन सा?
स्टैनफोर्ड
Stanford
प्रिजन
prison.
एक्सपेरिमेंट जिम्बार्डो
ओके
ना
वेट सर्च कर रहा हूँ
Yes.
स्टैनफोर्ड
हाँ
प्रिजन
स्टैनफोर्ड
एक्सपेरिमेंट.
प्रिजन एक्सपेरिमेंट जिम्बार्डो पर
It is
हाँ हाँ मैं
I
उसका
think Vsauce uploaded in the what is it called? This series. I forgot the name of the series.
हाँ
It's
कुछ
one of the episodes.
डॉक्यूमेंट्री भी है इट हैज इट्स ओन
Yeah.
वेबसाइट आल्सो.
He actually
फिलिप जिम्बार्डो.
interviews Dr. Zimbra himself.
किसने?
Michael from Vsauce. Wait, actually,
ओके ओके
वो
yeah.
उसका एक बुक है
हाँ हाँ
उसका
साइकोलॉजी ऑफ लाइफ ना
नहीं नहीं नहीं
लाइफ
नहीं
एंड साइकोलॉजी आई थिंक पॉपुलर है.
नहीं उसका जिम्बार्डो का एक इविल पे बुक है मतलब व्हाई डू नॉर्मल पीपल डू इविल थिंग्स इस पे. तो मैं वो पढ़ रहा था उसमें स्टार्टिंग में वो ये एक्सपेरिमेंट था स्टैनफोर्ड प्रिजन एक्सपेरिमेंट काफी
हाँ
काफी
अरे
ज्यादा.
मैं उसका ट्रेलर देखा भाई.
उसका नाम क्या था यार शिट एक सेकंड फिलिप जिम्बार्डो ना एक मिनट सर्च करता हूँ उसका काफी फेमस बुक है.
Okay, yeah, I got it. It's Mindfield episode, season 3, episode 4. Vsauce made an entire documentary on it.
द लूसीफर इफेक्ट है उसके बुक का नाम.
हाँ ब्रो तुम हॉरर मूवीज देखते हो क्या?
No, I absolutely hate horror movies because मैं बहुत ज़्यादा से like वो हो जाता हूँ and मेरा then it just like keeps on just क्या बोलते हैं it keeps me stimulated for like months on end because I
जस्ट
just cannot forget it.
कॉन्टेक्स्ट में लाइक एक बार मिस्टर को शायद किसी ने बुलाया था वॉच करने के लिए मूवी कोई हॉरर था ही जस्ट केप्ट इट ऑन वॉच एंड देन वेंट टू स्लीप और समथिंग.
नहीं मैं डिस्कॉर्ड कॉल ज्वाइन किया एंड आई जस्ट डिफेंड.
अरे डूड ये हॉरर मूवी देखने का एक ही तरीका होता है साथ में सब दोस्त बैठो और एक रूम में ठीक है प्रोजेक्टर पे चलाओ बहुत
Actually,
मजा आता है.
that's
वो
how I
कॉमेडी
watched.
हो जाता है फिर.
That's how actually
वो
how
हाँ
I
कॉमेडी
watched
मूवी
Annabelle.
होता है.
Annabelle was the
That's
last
a
movie
way
I
of
saw. and मुझे
reducing
पता
the
नहीं.
trauma.
इट चेंजेस इनटू कॉमेडी फ्रॉम हॉरर.
लाइक एक दोस्त को जो बहुत फटती है उसकी बहुत ज्यादा फटती है तो उसको देखते ही हंसी आ जाती है कि क्या होता है इसका.
ये कैंपस मतलब also like horror movie अगर अच्छे से enjoy करना है watch it alone at 3 AM without lights.
नहीं ये सब डेयरिंग स्टंट नहीं करना.
ये पता नहीं for some reason स्कूल में हमें बहुत नशा चढ़ा था ये करने का. And उस टाइम पे कुछ तो सीरीज आई थी इंसिडियस आई थी क्या पता नहीं.
अरे वो याद है क्या ब्लडी मैरी वाला कुछ तो रात को बाथरूम में कुछ तो कैंडल जलाओ तो पीछे भूत आ
बाथरूम में जलाने की जरूरत नहीं है.
नहीं नहीं वो कुछ तो स्पेसिफिक था उसमें लाइक तुम बाथरूम में जाओ कुछ तो किसी टाइम पे और कैंडल जलाओ और तुम्हें
ब्लडी मेरी बुलाना.
हाँ राइट तो पीछे आ जाएगी वो अपेरेंटली.
Yeah, we tried that in train. It was fun.
मैं 3 AM जग के इतना एडजस्टेड हो गया हूँ घोष डोंट स्केयर मी एनीमोर.
इसको कंप्यूटर लैब में जाके देखते थे इंसिडियस चैप्टर 1 चैप्टर 2.
अरे सबसे टची हॉरर मूवी मतलब हमने केजीपी में जो देखा था वो इट था. इट बस
भाई
जंप
क्या
स्केयर है
बात
उसमें.
कर रहा है. इट अच्छा है उसमें बहुत
नहीं
ज्यादा जंप
यार,
स्केयर है.
बस जंप स्केयर है उसमें और कुछ लाइक वो इम्पेंडिंग ऐसे सस्पेंस नहीं है उसमें बस जंप स्केयर है. मुझे
इट का बेस्ट पार्ट था हम लोग देख रहे थे प्रतिम के घर पे कोलकाता में कोई रहता नहीं है तो बस हम लोग थे. दिस इज द फर्स्ट टाइम वी गॉट ड्रंक इन केजीपी. देख रहे हैं वो इतना हरामी आदमी है उसको पता नहीं है वो हॉरर मूवी देख रहे हैं. वो रैंडमली गेट पे खड़ा हो जाता है अंदर स्टेयर कर रहा है भाई हम मूवी देख रहे हैं विदाउट रियलाइजिंग कि हमारी फट रही है अंदर बिकॉज़ ये बंद है.
अरे शिट रिकॉर्ड हो रहा है.
क्रॉप कर लगा.